Okay, good afternoon, everyone. Welcome to today's online session for Geotechnical Engineers. My name is Daryl Saraspe, and I'm an engineer with MIDAS, and I'll be giving the presentation today. So today's session, the first session, will be an introduction of numerical analysis for geotechnical applications. Okay, so first I'd just like to go over the learning objectives. So at the end of this session, we'd like all participants to develop an understanding of the applications of numerical analysis in the geotechnical engineering industry. Also, we'd like to have them gain an understanding of the overview of the theoretical principles. So we'll be reviewing theoretical principles for both conventional methods for geotechnical analysis as well as finite element analysis. And then also, we'll be going over a comparison of various conventional methods for geotechnical design. So we'll be going over the strengths and shortcomings of each of these methods to help you gain a better understanding of the tools that are at your disposal. So here is just an overview of what we'll be going over. So today's session will be split into four different sections. First, we'll give just a basic background of geotechnical analysis, different projects that are out there. And then we'll be going specifically into an application of numerical analysis. We'll be going over the fundamental concepts of numerical analysis, why we need it, and certain parameters that need to be taken into account when performing it. And then we'll be going into a study of numerical analysis specifically as how it relates to geotechnical engineering. So we'll go back to the different geotechnical problems that are out there, and we'll discuss the solutions that numerical analysis provides for it. And then last, we'll be going over case studies, specific projects where numerical modeling was used successfully to gain solutions for geotech projects. Okay, so chapter 1, here's just a breakdown of our first chapter. So we'll be going over the different categories of geotech problems. We'll be going over widely accepted or widely used approaches to solving these problems. And then we'll compare these conventional methods and sort of discuss their strengths. So first, different categories of geotechnical problems. So here are different types of geotechnical structures that are commonly designed by engineers. So you should all be familiar with these structures: foundations, retaining walls, deep excavations, dams, slopes, etc. So over the course of these 8 sessions, we'll take the time to go into more detail about each of these structures and how numerical modeling can be used to attain design solutions for them. And then also related geotechnical problems. So along with these structures, there are certain analyses that need to be taken into account. Slope stability, earth pressure, settlement, seepage, etc. So once again, over the course of these 8 sessions, we'll delve into greater detail about these various problems and how numerical modeling is used to design for these problems. So there are 3 main methods for solving geotech problems. First, there are closed-form solutions, or also known as conventional or analytical methods. These are the most widely used solutions. I'm sure you're all very familiar with them. As you know, they require the many assumptions and simplification of project geometry in order to make things easier, in order to simplify the analysis. So Terzaghis 1D consolidation and foundation settlement are just 2 very common examples of closed-form solutions for geotech analysis, and we'll be discussing these along this length of this chapter. And then numerical methods. So numerical methods will be the focus of these 8 courses. So as you can see, there are various sort of numerical methods that are out there, but the ones that we'll be focusing on the most will be the finite element modeling and numerical modeling programs. So one of the main benefits of numerical analysis is that it gives you more sort of detailed results, but it also requires the use of numerical modeling programs, which we'll give formal training for in these sessions. And then last, empirical methods, which relies on field testing, the use of geotechnical equipment to monitor the data. So this is essentially where all of your parametric results come from, just based on lab studies of soil and project data. Okay, so first let's go over foundation type problems. So as far as empirical solutions for pile foundations, there are 2 sort of main stress tests that are performed: total stress and effective stress, depending on whether or not your soil is saturated. But as far as total stress methods and effective stress methods, essentially what they do is they'll take these piles out to the project site and they'll put them under compression and lateral loading tests to see how the soil reacts. So this is a very reliable way of doing the analysis for foundations, but unfortunately it's very costly and time-consuming. As you can imagine, it takes quite a bit of time to take all the materials out there. It also takes time to run the tests. So in order to circumvent this process, various theoretical methods have been developed to make it more easy for engineers to do their pile foundation designs, especially for group pile foundations. So for example, Feld's rule and the converse Labar formula are two of the main sort of methods used for group pile foundation analysis, as well as block failure criteria, which needs to be taken into account for group pile foundations. So if you go to this, if you refer to this this image here, as you can see, one of the main strengths of pile foundations is that it distributes the weight along a greater isobar or a greater area of soil, thus making the foundation more stable. But another thing that needs to be taken into account is how the isobars for the individual piles tend to merge at certain points, creating highly stressed zones. So this is something that needs to be taken into account, and we'll be going into a greater detail about pile foundation analysis in our next session. But these are just things to look out for, and I'm sure you're all familiar with it when you're doing group pile foundation design. So numerical analysis, one of its main advantages for foundation design is that it provides alternatives to overcome difficult problems. So for example, if you have asymmetric group pile foundations or configurations that include many dozens of piles, numerical analysis would come in especially handy. And then it's absolutely necessary to cross-check with field data and analytical methods. That way you can sort of double-check to make sure that your results are reasonable. So you don't have to do the entire project with field data or analytical methods. What you can do is you can do the entire project with FEA software or numerical modeling programs, and then you can cross-check certain points or critical points using analytical methods and field data, just in the interest of time. Okay, so slope stability method. So the most common or the most widely used method to solve slope stability problems is the limit equilibrium method. Essentially how this method works is that engineers will just take a slope and divide it into several vertical slices, and then just using physics they're able to determine the free body diagram or the forces acting on each of these slices. And then through the use of integration equations, they're able to determine the strength reduction factor as well as the factor of safety. So this is especially useful for simple slopes or slopes that have very simple geometry. But one of the shortcomings of this method is that for slopes that have complex 3D geometry, it would require the use of something more sophisticated. That's where numerical modeling comes in. So once again, we have another session that's specifically geared towards slope stability problems and the different methods involved to solve them. And we'll go into greater detail in that session. But this is just sort of, I guess, an overview of what you already know, just to sort of double check with you, just to make sure we're all on the same page. Okay, so retaining wall problems. So as you can see in this slide, I've divided the conventional method and numerical method into separate sort of columns here. And under the conventional method, I've included all of the sort of design segments that the conventional method is typically used for. So as you can see, heel width, overturning, toe design, external and internal stability, etc. Those are all fairly simple portions of the design of retaining walls that can be analyzed with just very simple equations, simplification of segments, etc. But for the numerical method, if you look at the list of segments of the projects that are analyzed with the numerical method, as you can see, these are a bit more complex. For example, interaction between the structure and the backfill, evaluation of failure mechanisms, construction stages. So these are sort of the more complex or the higher end portions of retaining wall design. So essentially, if you have larger retaining walls that are larger in scope, you would need to do these types of analyses. Whereas if you had simpler, sort of smaller scale retaining walls, then these would suffice. But in essence, it's always best to have both methods at your disposal. That way, if you ever needed to perform maybe some higher end analysis for your wall, you'd be able to run that using the numerical models. Okay, now excavation problems. So once again, I've divided the sort of different applications according to the methods that are used for them. So first, let's take a look at the conventional method. So simple beams and continuous beams both fall under the conventional method section. And the main thing to remember is that they're suitable for shallow excavations. So for excavations that are smaller in scale, that don't require a great deal of support structures, you can use the conventional method to gain a fairly accurate approximation of the stresses acting on your walls and the stability of your structures. But as you go into greater excavations or larger scale projects, you'll find that the conventional method won't suffice. You'd need earth pressure method as well as soil structure interaction. So as far as the earth pressure method, as you can see, it's suitable for deeper excavation and for structural results in the passive zone. So as you get deeper excavations, you would need elastoplastic beams to account for sort of bending in your structure. With a conventional method, you could just assume that it will be rigid just because there isn't enough soil pressure to create deformation or significant bending moments. But with larger scale projects, that assumption, you can't make that assumption, so you'd need something more in detail. And then for soil structure interaction, which is sort of the highest level of analysis for excavations, as you can see, it's done with numerical modeling programs, and it can consider adjacent structures. So say, for example, you're doing an excavation, but there's a nearby structure, and you want to ensure that your excavation doesn't significantly reduce the stability of that foundation. You would need to do a numerical analysis because neither the earth pressure method or the conventional method would be able to account for that. Also, you can do soil structure interaction, which is a study of how foundations in direct contact with the soil react when placed under, for example, seismic loading, which is a very sort of specialized topic, which is essential for larger scale projects. And we'll get more into that sort of later on in this session. Okay, so just a summary of this chapter, just some main things to remember. Numerical analysis provides alternatives for difficult problems. So as projects get larger in scope or become more complex in detail, or as more sort of problems arise, numerical modeling becomes more and more prevalent. Also provides mutual supplementation to obtain detailed results. So say, for example, if you have maybe a conventional project that you've done with, that you've analyzed with an analytical method, it always helps to have another method against which to measure your results, just to make sure that you calculated it correctly. So the numerical modeling method could be used to double check that, and also to check for maybe certain things that you couldn't account for with the conventional methods. And we'll discuss more in detail about how these numerical methods can obtain other results in future sections of this presentation. And then also it provides an advanced approach that can consider more variables. So as I mentioned before, there are certain other variables that conventional methods can't take into account that, depending on your project, you would want to take into account using numerical modeling. So numerical modeling doesn't give a total or an exact solution. What it does is it supplements the solutions that you already have. And it's always best to find the best solution using everything that's available to you. So for those of you who are new to numerical modeling, what we'll be doing in this session is we'll be discussing how it's a tool that could be especially useful for you to sort of widen your design capabilities and to help you, work more efficiently, and to maybe even take on some projects that you weren't able to take on before because you didn't have the tools required for it. Okay, so moving on. So Chapter 2, the application of numerical analysis. During this chapter, we'll go over why specifically we need numerical analysis, why it's important, why you would want to use it for your own work processes, and what we can obtain from numerical analysis as far as the results, results that are unique to it, results that could help you design for greater levels of safety, and also to cut costs, to work more economically. And then how to utilize your design parameters. So when running a numerical analysis, there are certain parameters that you need in order to do it effectively, and we'll go over all of those here. And then things to be considered in numerical analysis. So numerical analysis is a unique sort of analysis method in many ways. It has sort of many unique considerations and things to keep in mind, and we'll go over those as well. Okay, so why do we need numerical analysis? So here are various reasons that we've outlined. So first and foremost, there's no limitation of the modeling. So any type of 3D complex geometry you could create in a numerical model. So for example, as I said in the previous section, analytical methods rely heavily on simplifications, assumptions, whereas numerical modeling doesn't rely on those. You can be as specific as you need to be, which is especially useful for projects that have special considerations that can't be ignored. So then stress deformation relationship. Numerical modeling is especially useful for gaining or for calculating soil stresses and structure stresses, as well as displacements and deformations of structural and element properties. Soil structure interaction, once again, this is especially useful for seismic analysis, and we'll go over more detail into that. Efficient parametric studies for optimum design. So we'll go into how later on in this session we'll discuss parametric analysis and how you can use it to go over, for example, to create several sort of design solutions and compare them against each other to find out which design is not only safe but also most economical. And then reflection of construction stages. So various construction stages. For larger scale projects that require multiple construction stages, numerical modeling can model each of those stages very efficiently. And then various analysis types are available to you. So among the unique analysis types that are available are seismic and coupled, which analytical methods can't nearly handle. And then also various constitutive models for soil. So numerical modeling programs typically have databases of constitutive models at your disposal so that you can have a constitutive model that best suits your project just on hand. So now I want to just very quickly go over a case study here, the Carsington Dam in England. So this was a dam that actually failed back in 1984, and initially it was analyzed using the limit equilibrium method. And as you can see, they had a minimum factor of safety of about 1.4, but over time the factor of safety was reduced to 1.2 by pre-existing shear surfaces, so shear surfaces that existed prior to their study of it. And then eventually, over time, it reduced down to 1.0, and eventually it failed. So the initial failure was due partly to periglacial solifluction. So essentially what that means is that there was water in the pores of the soil, and because of just the region it was in, that water would freeze and unfreeze over certain periods of time. And as you know, when water freezes, it expands. And that expansion caused, a series of stress along certain points of the slope, which caused it to weaken, which caused the minimum factor of safety to weaken, and which ultimately led to its failure. So as engineers were studying, the cause of its failure, they realized that through using a numerical modeling program, that it could account for periglacial solifluction, or they could account for the changes in pore water pressure over, the changes of the seasons. So that was a big sort of breakthrough with finite element modeling. It was, this is one of the many projects through which engineers found that numerical modeling provided, a unique solution that wasn't possible with conventional solutions, and it was a solution that would have prevented the failure of this particular slope. So that's just sort of a real-life case study of how numerical modeling can be used to give you solutions that are necessary and essential. So that's why we'd encourage all of our clients to use numerical modeling just to back up their conventional methods. Okay, what can we obtain from numerical analysis? So from the ground specifically, from soil elements, we can obtain the deformation, settlement, and horizontal displacement. So if you look at these two models here, these are just examples of post-processing models for numerical modeling. And as you can see, via these contour graphs, we're able to see where the displacement is critical or at its maximum. So that would be those red points here. So that's something that's very unique to numerical modeling, is that you can directly just calculate the displacements as your soil is given more pressure or given more loading. The numerical modeling program can calculate just to what extent the deformation will be. and then the stresses, earth pressure, principal stresses. So you can analyze the soil itself to see how the shear and axial strain increases over loading, over different sort of weather conditions, such as changing in water levels, etc. And then failure of the element and factor of safety. These are two things that can be analyzed directly just from the numerical modeling program itself. Okay, now for geotechnical structures, numerical modeling can be used to calculate the axial forces, the shear forces, and the moments. So if you refer to these two images here, these are two images of some geotechnical structures. And once again, it uses these contour diagrams or these contour graphs to show you where the critical areas of bending moment are, or axial forces for these piles here. So through numerical modeling, you're able to take these large structures, analyze them very thoroughly, and then just at a glance, you would be able to tell where your critical areas are, maybe points that would be of interest to you, points that you really need to look out for when you're doing your design to make sure that they meet safety standards. And of course, axial stress, shear stress, and then relative displacement. So the displacements or the deformations of these various structures could be calculated as well. Okay, how to utilize your design parameters. So here's some things that you need to have ready for you before you begin your numerical modeling. First, you need to have your drawings of your structures, as well as a soil profile. So these two things are key. So it's important to have these two parameters ready for you before you begin your numerical modeling. And then another key thing that you need to take into account is whether or not you want to do a 2D section view or a 3D plan view plus a section view. Now there are certain advantages and disadvantages of each, but essentially simpler, smaller scale projects with simple geometry would best be done with 2D analysis, whereas larger scale projects with more complex geometry would best be done in 3D. And we'll go more into detail into this later on. But just keep in mind that 2D analysis is much faster, it's much more efficient for smaller projects, whereas 3D analysis takes a much longer time, but it's something that needs to be used for larger scale projects. And then the level of detail, shape of modeling, the type of analysis you want to do, make sure to have these parameters sort of defined beforehand so that you can sort of plan out how you want to do your numerical modeling. Okay, and then make sure to have your soil profile ready as far as your strata, but then also your various parameters. So these should be nothing new to you guys. For example, relative density, your SPTN values, consistencies, internal friction angle, and then also, for example, if you're doing like a seepage analysis, you need your pore water, or not your pore water pressure, but your permeability coefficients. So just make sure to have all of this data ready so that you can input it into the program. And then also make sure to take your geometry shape into account. So the geometry shape, the shape of your structures or your project site. Input parameters include the soil parameters that we just discussed, boundary conditions, which I'll discuss in the next slide, and then also analysis options, which will be discussed in the next chapter. And then engineer's knowledge. This is probably the most important of all three. So engineer's knowledge includes the engineer's working knowledge of the tool, in other words, the numerical modeling program that he's using, as well as the project itself. So it's important, or it's essential that the engineer has a very clear working knowledge of the program that he or she is using, as well as the project with which he or she is involved. A lack of knowledge in either of these sort of areas could lead to a lot of problems, a lot of holdups. So it's just important that the engineer learns as much as he or she can about the project itself, as well as the numerical modeling program. And this is essentially what this course is for. We understand that engineers, they're very sort of professional when it comes to learning about the project. They have all the parameters ready. They know everything that needs to be done. But when it comes to numerical modeling programs, that can be a bit of an issue because there's no formal training available. So these courses, what we'll be doing is we'll be helping you all to develop a better understanding of numerical modeling programs, how to use them, so that you can be more confident with your numerical analysis. Okay, so this is just a sample of geometry shape and sort of the boundary conditions involved with it. So this is a sample 2D excavation model. So as you can see, each of these boundary conditions is a factor of the depth of the excavation. So it's important to remember that when you're creating your boundaries for your numerical model, that you want it to include a large enough portion of your project so that everything within a certain area is covered. But you don't want to make it too big, whereas the analysis would run longer than it would need to, and it covers portions of the project that really don't need to be considered. So we'll discuss more about creating your boundaries later on, but just keep in mind that your boundaries are very important, and when you create your boundaries, it should always be a function of your project conditions, your project site. Okay, so input parameters, garbage in, garbage out. So this is one of, I'm sure for those of you who've been around numerical modeling programs before, you've heard this term. Essentially what this term means is that if you put, if you have a bad, or if you have like post-processing results that don't make any sense to you, that are useless to you, it's a product of bad input. So somewhere along the line there is a mistake in the input analysis, or the input that was created by the engineer. The way that I like to think about it is just through, for example, the analogy of a really great car. You could have one of the best cars in the world, one of the best cars available to you, but if the driver doesn't know what he or she is doing, then that car isn't really of much use. The same applies to computer software. So you could have one of the best, numerical modeling programs that money can buy, but if the engineer doesn't fully understand how to use it, then that program isn't very much use. In other words, a numerical modeling program is really only as good as the engineer that uses it. So if you ever have, any issues with your post-processing data, essentially, there's not a problem with the program itself. There's something wrong with the input that you've created. So just sort of keep that in mind to take accountability for the post-processing results that are created. So soil parameters, I won't go into too much detail. I'm sure you're all familiar with these parameters. These are all things that you need to have on hand and ready for your project. Boundary conditions, you need to have an understanding of the various constraints, seepage and seismic types boundaries. And then analysis options, you need to know whether your project will be drained or undrained. So if it's drained, you'll need to account for effective stress, but if it's undrained, all you need to worry about is total stress. Okay, so engineer's knowledge. So here's some things that we encourage all engineers to ask themselves before they run their numerical analysis. So first and foremost, do I understand my tool correctly? So do I understand how to use the software? Do I understand where to begin? If you don't, it's going to lead to technical problems. So if you don't fully understand your tool, there's a number of things you can do. You can check the manual, you can call technical support, but don't just start your project. Just make sure to learn as much as you can about your tool, or as much as you can about what you need for your tool before you get started. Do I assess input parameters based on geotechnical knowledge? So in other words, sometimes engineers get sort of caught up in the trap of just entering parameters but not fully understanding what they're entering. They just maybe saw a tutorial, or they just saw in a manual certain numbers go here, but they don't really understand what the numbers mean. So it's imperative that the engineers understand every input parameter that he or she is entering, so that if there's a problem, they can understand what these numbers actually mean. So can I explain the result behavior in geotechnical terms? So a lot of times numerical modeling programs will give us these results, but we need to sort of interpret them as geotechnical values, or in order to explain them to clients or to supervisors, we need to take these terms and sort of interpret them in a way that would make them understandable to those working in the geotechnical engineering industry. So we'll go into more detail about this later on when we discuss post-processing and result extraction, etc. Can I define the reliability of the results? So even though you got, say for example, you got results that are satisfactory to you, it's so important to understand the limitations of the input parameters and analysis options. So even though the results may be good, just keep in mind that the results aren't absolute. There may be certain factors that need to be accounted for. Once again, these results, their calculations, their predictions, but they're not 100% reliable depending on the situation. So it's really important just to keep in mind certain other factors that could alter the reliability of these results. Okay, so here's just a quick summary. Make sure to think why you are doing the analysis before you build a model. Make sure to realize the reason behind the modeling, the reason behind the analysis. Always keep the end goal in mind. interpret analysis results properly. So we'll go more into detail about how to do result extraction, about how to interpret or translate result outputs into geotechnical terms that everyone will be sort of on the same page with. So numerical analysis reflects the design process. Utilize your design materials and find correlations. So numerical modeling is especially useful for design, for optimizing design, and we'll get more and more into detail about this as we progress with the course. And don't forget, garbage in, garbage out. In order to get quality results, quality outputs, you need to put in quality inputs. You need to understand what exactly you're putting in. Okay, now to Chapter 3. So in here I'll discuss the importance of soil parameters, how a study of the soil and understanding of soil behavior is key to numerical modeling. Constitutive models, the various constitutive models that are available to you, and how to understand when you need them or what types you need for your particular project. And then various analysis types to solving geotechnical problems. So I'll just touch upon the different analysis types that are available to you and the different problems that they're sort of related to solving. So what is the definition of a soil parameter? Essentially, it's a physical characteristic for soil to reproduce ground behavior mathematically. So types of soil parameters. So essentially we have different types of soil out there, and we have these different parameters to predict their behavior. Everything from unit weight, void ratio, elastic modulus, cohesion, friction angle, etc. And each of these parameters relates to a different sort of category. So the most commonly used parameters are the naturals, which are just how much it weighs, the water content. These are typically used for all projects. And then as you get more specific, the parameters become more specific as well. So elastic modulus and Poisson's ratio, those would obviously be used for like foundation type analysis. Strength and cohesion angle, cohesion and friction angle would be used as well for foundation types analysis, as well as excavations. And then seepage would be used. So for example, the permeability of your soil, the soil water characteristic curve, these would be used for embankment and dam designs. And then dynamic, obviously shear modulus and damping ratio would be essential in order to account for seismic loading. So characteristics of behaviors. So we need a decision of parameters, whether they're strain dependent or stress path dependent. So let's go into more detail about this. So one of the things to remember about the behavior of soil is that it's nonlinear, which makes it harder to predict. So if you take a look at this graph here, as you can see, as axial strain increases, the deviatoric stress will increase linearly up to a point, and then it'll start to taper off. And usually what happens with soil is it'll reach a yielding point, and then it'll start to go down, it'll start to soften. It's this type of behavior makes the design of geotechnical structures a little bit more complex, especially for larger geotechnical structures where the strain would reach a point where this yield point would be reached. As you can see, the nonlinear behavior relates to the shear modulus as well. So it's an important thing to keep in mind, this sort of nonlinear behavior. And as the load increases, it'll reach a point where the soil will reach a point where it starts to actually lose its strength. Okay. Another sort of complication of soil behavior analysis is that certain structures create different stress paths or stress curves. These what these lines here represent. So for example, let's take a look at this embankment image. As you can see, the soil would be uniform all around, but the stress curve is different on each part of the soil. So if you here, this would be like axial loading, here this would be shear, and here this would be like lateral loading. And because the loading is different on each portion of the soil, you would need a different sort of test to predict its behavior. So for the axial strain or the axial loading, you'd need a triaxial compression test. For the shear strain, you'd need a direct simple shear stress. And for the lateral loading, you'd need a triaxial extension test. So each of these tests are different, and they get 3 different nonlinear results. And all 3 stress tests would be needed for this one project because the different stress, the stress is being applied in each of those ways. And the same for a loaded wall. Here's the stress curve. Here the loading would be, you'd need the direct simple shear test. here you'd need, the loading would be lateral, so you'd need a triaxial extension test. So once again, as you can imagine, this becomes even more complex as you have different soil layers. So you'd need, with each soil layer, you'd need another set of 3 tests for like this embankment one. Then for a drilled shaft example, for example, you have your compression test, you had an uplift test, which would require this direct simple shear test, and then lateral test as well. So let's take a look at their different. So here are sort of 5 different tests that have been run for the same soil. And as you can see, each of the results is different, and they're all nonlinear, which makes sort of your soil parameter input so important. And then another thing to keep in mind is that hard rock is fairly simple to predict because, as you can see, as the strain increases, the stress increases linearly. So just using this type of relationship, you'd be able to very easily predict the behavior of your hard rock, which makes sort of rock foundations ideal for certain projects that would benefit from having especially simple calculations for stability of the foundation, or stability of the ground foundation. Whereas with soil, it reacts in one of 2 ways. So it'll increase the stress will increase linearly up to a point, and then it'll reach what's called the elastoplastic range. This is the point where soil would cease to sort of retain its shape after, say for example, the load was removed. So once it reaches this point, one of 2 things happens. Either the stress decreases, it loses strength, and it begins to taper off, or it'll harden, and it'll continue to increase its strength, but not in a linear way. It'll sort of taper off as it increases. So this elastoplastic range is very critical to sort of predict where exactly or when exactly you would reach this range, and to predict the strength of your soil afterwards. That's why numerical modeling is so sort of key, is that it can take the various equations that are related to each of these soil behaviors. So for example, for this line, for each line actually, you need a different set of equations. You need to sort of break it up. But with numerical modeling, all those equations can be inputted, and you'd be able to account for nonlinear behavior in a much more efficient way than doing it through a spreadsheet or by hand. Okay, now let's talk about various analysis types for geotechnical problems. So over the course of these 8 sessions, we'll be going into great detail about all these different analysis types: static analysis, construction stage, seepage, slope stability, seismic, and then coupled analysis, which is something that's very unique to, or actually seismic and coupled analysis, both of which are extremely unique to numerical modeling, extremely useful for certain project types. Okay, so first for static analysis. So this would be, for example, a final stage analysis without a construction stage. In other words, maybe you have like a smaller scale project or simple project where construction stage analysis wouldn't be necessary. You could just design for the final stage. So the analysis itself is very simple. It's usually very easy and fast. It's very similar to the analytical method. And it's always a good practice. If you look here, these are just some examples of analytical methods that are used for static analysis, and these are good. These are just sort of a good sort of benchmark that you can use to make sure that your numerical analysis for static design went through all right. So what you can do is you can just check these results against the results you got for your numerical modeling analysis, and since these are fairly simple and straightforward, you can predict. You can have reasonable accuracy with them, and you can compare them directly against what you have. And if they're within the same range, the results for your numerical analysis and the results you get from these 2 tests, then you can say with greater confidence that your calculations are correct. And then construction stage analysis. So we'll go into more detail about this particular project during the final section of this lecture. But one of the great sort of advantages of a construction stage analysis is that you can take a large, complex, lengthy project and simplify it by dividing it into a number of time-dependent sections. So with this particular project, the excavation was divided into a series of segments, and for each sort of series of segments, a construction stage was created to view how over time the excavation would affect the nearby structures. For example, this nearby foundation, this nearby retaining wall, believe there's a street over here. So you can see gradually how the stability of these neighboring foundations and structures was influenced by the excavation. And then likewise, as the foundation itself was created, you could account for temporary support structures. You could see how the loading on the foundations increased over time. Also, you can see how the loading upon the soil increased over time. You could account for nonlinear behavior for the various layers. So this was a very large, complex project, but by breaking it up through construction stages, you were able to simplify it. And so projects such as these are very difficult to cover by analytical or empirical methods. So numerical modeling software or programs is especially useful for these. And then seepage analysis. So here we have just a couple of pictures of some results or result model files for a seepage project. So here's like an embankment that shows how the total head changes from one side of the dam to the other. And then also 3D seepage results and flow paths. So with seepage analysis, you can figure out the groundwater levels, flow paths. You can account for rainfall. So for example, if you want to see how the pore water pressure, how the water flux or the nodal head changes with different sort of levels of rainfall. Say, for example, maybe 3 days of rainfall, you want to analyze how those results change. You could do so through a numerical modeling program. Also rapid drawdown. If this water were to be drained very quickly, you could see how that drainage would affect the stability of this dam. Once again, something that's very unique about numerical modeling is that you could model time-dependent behavior such as this, which would be critical for dams. And then slope stability analysis. So numerical modeling programs can be used to do the limit equilibrium method. So for simple, straightforward slopes, that's usually your best option. But at the same time, it's also good to check these results through the strength reduction method, or excuse me, the shear strength reduction method, which utilizes finite element analysis to analyze the stability of the slopes. So that way you have two analysis types to check against each other to make sure that you did them correctly. And then also for 3D slopes that have more sort of intricate or complex geometry, you could model with a numerical modeling program. You could model these in 3D, and you can take into account how this asymmetric geometry would affect the stability of your slope in 3 dimensions. And then seismic analysis. Here I've just listed out the different analysis criteria. For example, your dimensions. 1D would be for 1D ground response to analyze how your soil would respond to seismic loading. And then 2D and 3D soil structure interaction to analyze how your foundation structures would react by being placed in direct contact with the ground. Stress-strain relationships, for example, linear. Linear analysis is fairly simple because it falls within the elastic range. In other words, your soil or your structures are still being loaded to a point where they can still return to their original shape. But for nonlinear analysis, numerical modeling becomes more and more prevalent because of the complexities that are involved. And then excessive pore water pressure leads to a phenomenon called liquefaction. So for those of you who are working in California, I'm sure you're very familiar with liquefaction and the complexities that come with it. For those of you who aren't too familiar with liquefaction, essentially what it is when there's water in the ground and the ground and the water is subjected to seismic loading, the ground itself can act as a liquid, which leads to a lot of considerations to be taken into account for seismic loading. So we'll get more into these types of phenomena or these types of design criteria for our seismic analysis course, which will be later on. But these are all just things to keep in mind for your seismic analysis. And then last we have coupled analysis. So if you look to the bottom here, I have 4 different examples of coupled analysis in use. And essentially coupled analysis is just taking 2 different analysis types that are interrelated and using them for the same project. So let's take a look at this dam here. So as you can see, this dam has a water level that's much higher on this side than on this side, so naturally there's going to be some flux taken into account. So you'd have to do a seepage analysis. But the pore water pressure would also have an effect on this consolidating layer, this clay layer here on the settlement. So in order to account for the pore water pressure loads on the settlement, you need to do the seepage analysis and then model those loads into the consolidation or the settlement analysis. So using numerical modeling, you'd be able to run both analyses on a single file. The same applies to like a deep excavation. So for example, you're excavating over here, you're putting up your retaining walls, but because of the poor water pressure due to this water level here, you have some additional loads that you need to account for. So what you would do is you'd run a seepage analysis to generate your poor water pressure loads, and then you'd apply those loads to your excavation analysis. So essentially what coupled analysis allows you to do is to factor in a different analysis type onto the same project, or to factor two different analysis types in the same project. So for example, the same holds true for this retaining wall. Poor water pressure loads in addition to in situ stress loads or soil loads would need to be modeled on the same retaining wall as well as this tunnel. So we'll get more and more into detail about coupled analysis later on in this lecture, but that's just a general overview of what coupled analysis is and why it's important. And once again, numerical modeling provides some very unique and powerful solutions for coupled analysis. Okay, so now we'll just do a couple of case studies. First, I have a pile foundation that I'd like to go over, then a deep excavation, and a ground settlement type project. Okay, so our first case study is the Pentaminam Tower in Dubai, which is a very high-profile, high-end project, and the design of the foundation was quite complex. So as you can see, this is a sort of the cross-section or the soil profile that they had to deal with. It had several different types of soils and hard rocks that they needed to account for, that these piles, or that the piles would be sort of placed against. So numerical analysis was essentially used to evaluate the overall piled raft response under various static and wind loading combinations, as well as and some techniques were used to optimize the design foundation, including the preliminary pile testing. So here's just a picture of the finite element model that was used. As you can see, it's very intricate. It included 9 levels of the superstructure as well as 6 basement levels. And the settlements were obtained from different types of soil models, both linear and non-linear. So as you can see, the pile arrangement was very complex. Included, dozens of different piles. And then using construction stage analysis, they were able to see how the construction or the development of the foundation was able to affect nearby structures or nearby foundations, excuse me. And they were able to see how the increasing load was affecting the piles as well as the foundation itself, or the soil itself. So a substantial amount of testing was carried out for the design of the Pentaminam Tower foundation. This included soil and rock testing as well as a comprehensive pile testing program. So as you can see here, for the nonlinear soil, the settling was much more, I guess, a little more severe. Because nonlinear soil, as you know, if it once it passes that yield point, it begins to weaken and taper off. Whereas linear soil was stronger and more resilient towards the loading. So this was something that needed to be taken into account, especially because it had linear and nonlinear soil. So they needed to predict or to calculate how the soil would react to increased loading as the foundation was built and the superstructure was built. So in addition, complex geotechnical finite element analysis has been carried out, which has been validated using standard geotechnical calculation techniques. So it's important to note that even though they used finite element modeling for this, they didn't abandon conventional methods. Essentially what they did was they used finite element modeling for the bulk of the project, but for certain critical points they would check it against conventional methods just to ensure that their results were reasonable. And then the application of such testing and analysis approaches has resulted, in a cost-effective and optimized foundation design solution. So ultimately, this project was a success. They were able to, build it efficiently. It was able to pass all the safety regulations, and as far as I know, their budget, they met their budget. And then, so here's my next project, or my next case study. It's the Louisiana Bulkhead Project. So as you can see, here's just like a top view of the project site, and it involved the transportation of these large ships here. So the client for this project was responsible for the bulkhead itself, and the ships would be transported from the warehouse just over to the shore. So the trips would travel via these rail tracks, and because of unstable ground conditions, the consultant decided that additional piles were necessary to improve the ground conditions. So the new adjustments took into effect the settlement, and the software was able to analyze the ship loads through point loads. So here's just a cross-section as well as a top view of the pile arrangement. So as you can see, there were many piles were involved with the construction of this particular project, which required, which was sort of a natural choice to use finite element modeling software because of just the scope of this project and the complexity of the analysis that was involved. And the modeling itself was done section by section. So that's another key advantage of numerical modeling programs, is that you can take these large, sort of intricate projects and you can simplify them by breaking them down into smaller pieces. So the initial modeling began with the piles, and the surrounding structures were modeled first. The soils were modeled subsequently with the proper material properties, and the final steps were to create the top layers and the rail tracks themselves. So as you can see, they were able to do it piece by piece, and ultimately once they combined everything, they had this large, intricate project that they were able to build through a very sort of simple process. It was just a bit longer because the scope was larger. Here's just some model views of the completed project. So here's a cross-section or cut view of the stress model. So as you can see, naturally the stress would be largest at this point where the rail tracks are, where the point loads would be from the ships. And just through this program, they're able to sort of predict the maximum or the critical shear stress, not only for the superstructure, but also for the ground elements and the piles, and the axial loading for the piles. And then here's a displacement view of the piles, so they could see, or they could predict with confidence how the piles would deform or deflect as the point loads from the ships was applied to them. So in this project, the client placed the ship loads through the rail track, and the piles were all added in accordance to the ground condition study for the stability. So they had, all their soil parameters ready. They did all their soil studies. They were very, very detailed about that. And each load was taken as point loads to get a more practical result. And upon the finished analysis, the client found that the projected preliminary study was safe for construction. So with the piles improving the current ground conditions, they began to see if they could reduce the number of piles while maintaining the safety factor. So this was something that I had mentioned earlier about numerical modeling, is that it's it's very handy for design. So for example, as I said in this project, they found that their initial design met the safety factor requirements. So afterwards, what they did was they started to see if they could use maybe less piles while still maintaining that minimum safety requirement. That way they could continue to, not only maintain safety, but also cut costs to work more effectively to create more optimized designs. So that's another key advantage of numerical modeling in general, is that you can use sort of an iterative design process to create more optimized designs while still ensuring, safety, to ensure that your design still meets those design codes. So this is especially useful for, bidding for larger products or just bidding in general. You can submit more optimized designs, you can submit lower bids, with confidence because you were able to model it on the program, you're able to check it with your conventional methods. Okay, so my last case study is the Odeon Tower, which is a 49-story high-rise building in Monaco. So as you can see, it's assessment of ground surface movements, especially at adjacent buildings. So in other words, as they were building the foundation, as you can see, this is a very developed area, and in order to perform the excavation and to build a foundation, they first needed to make a study of the effects of this excavation on the nearby structures here, just to make sure that the stability and the strength of these foundations wasn't significantly altered or affected. And because this site had some, sort of complex asymmetrical geometry, it needed to be done in 3D. So, we went over this project before, or this part of the project before anyway, but it was done through construction stage analysis. They were able to sort of divide all of these different layers into sections. They were able to see step by step how the surrounding soils were affected by the excavation. So as you can see, there was a high school building nearby, as well as some adjacent building foundations and some streets. So just through this staged construction analysis, they're able to see how each stage of this excavation gradually affected these adjacent foundations. And then once the excavation study was done, once they were able to ensure that the retaining wall structures or their temporary support structures would be able to ensure the safety of the neighboring infrastructure, then they were able to design the foundation itself, along with the cable anchor system, which was necessary to ensure the integrity or the structural integrity of the foundation. So the retaining system and the adjacent buildings, are closely monitored in terms of induced movements. So the displacement fields predicted by this model were instrumental in defining the threshold values and action values, which allow for early detection or warning signs and timely response to any type of geotechnical hazards. So for this presented case, a satisfactory understanding of soil structure interaction, in other words, how seismic loading would, affect the foundation itself. So soil structure interaction and the way of the retaining system, it fulfills its roles. It can only be gained through 3D numerical analysis. So for this project, it was only the only real plausible or the most efficient solution would be to model it in 3D with a numerical modeling program. Because I'm sure, as you can imagine, with conventional methods, it wouldn't have been effective and it wouldn't have been accurate because of a number of factors, one of which would be the oversimplification of the geometry itself. So all this geometry was modeled in detail with a 3D numerical modeling program, and ultimately they were able to design successfully, and they were able to complete the project successfully with the help of this program. So I know that these three past projects are all sort of higher end projects. They're large scale. So numerical modeling was necessary, or was the best solution. But just keep in mind that numerical modeling can also be used for smaller scale projects or conventional projects. As I said before, it's very useful to use numerical modeling programs to check the results of conventional methods or to account for other factors. And because of the quality of the numerical modeling programs that are out today, you can run numerical finite element analyses very quickly, much faster than you could in the past because of various features that have been developed with the programs themselves. So I understand that all of you will be receiving free copies or free trial versions of MIDAS GTS if you don't already have it. And what we'll be doing and what we're looking forward to is teaching you how to use the program to do your own finite element modeling, and to show how maybe you can use it for some of your upcoming or current projects. So we look forward to going into more detail about that. So this concludes session 1. Once again, my name is Daryl Saraspe. I'm an engineer here at MIDAS. If you have any questions about this session, feel free to give me a call. This is my office number. And then feel free to send us an email at midasopt@midasuser.com. We're always sort of open to suggestions for improvement. So I hope you found this session beneficial and useful and informative. Just keep in mind that we've only scratched the surface here. We've still got 7 more sessions to go. And we look forward to going into more detail about the sort of the topics that we've introduced here today. So thank you again for your time and your attention. We look forward to meeting with you all next week, and feel free once again to contact us if you have any questions or if there's anything you'd like to see in particular for next week's session. So take care, and we'll see you again next week.